All right, welcome. Today we're going to be talking about filters. Filters are one of the more unique concepts in HELICS that enable some interesting capabilities for federates to interact together and incorporating some different types of scenarios into HELICS. So today we're going to be talking about what filters are and how to register them and program them and some of the capabilities of them. So filters are inline operations, and they can alter a message or event. If you remember, we've previously talked about message interfaces, and these are packets of information that get sent from one federate to another, and they can be altered in a number of ways. There's some pre-built filters in HELICS. These include time delays, randomly dropping, cloning, rerouting, and you can also specify custom filters. Filters are part of a core, and so their effect is not limited to local endpoints. So you can create a filter on any federate or core in the federation and have it interact with any other endpoint in the system. As an example, say we have a transmission network and it's sending data to an AGC controller. So a generation control algorithm is working on another federate. So data gets sent to the controller, and the controller sends control signals back to the transmission network to control the generation. If we just want to model a simple communication delay, we can insert a filter in this, and the filter can alter the time stamp of the messages so they're delayed by the time they get to the controller, and the same way on the path back. Now, if we want to do something a little more complicated, say we have a full communication simulation in the system, and what we want to do is have a packet translation that translates the message into a packet that the communication network can understand. Say it transmits, transmission network transmits data, but the communication network needs an actual data packet in some standardized TCP protocol or something along those lines. So we have a packet translator that translates the data to the appropriate packet, and then a rerouter which reroutes the signal, which would have gone to the AGC controller and now routes it to the communication simulation. On the other side of the communication simulation, it's sending the data out, which is now going to the AGC controller, and we have another packet translator that translates the standardized packet into something the controller can understand. And the same path can operate on the way back. And the point of filters here is that everything with the communication simulation can be done without having to alter anything within the transmission simulation or AGC controller. A filter has a couple different parts to it. There's a target, which is an endpoint in the federation somewhere. It can be a source or destination filter. Source filters will trigger anytime a target endpoint sends a message, and destination filters will trigger anytime a destination endpoint receives a message. The operator is a processing function that gets done on the message. So you can create a custom function for this, or there's several predefined ones, and we'll talk about those a little more later. They can include cloning, delaying, dropping the packet, or rerouting. Just as an example, say we have a grid model interacting with a house model, and that actually talks through the value-based interface. The grid model can also interact with a controller via a message interface. And this all interacts across the HELICS communication system internally. A communication simulation, for example, NS3, can be inserted into this to intercept the control messages, process them, send them through a full communication simulation with delays and other factors that may affect the communication simulation, and then send the messages on again to the controller. So this is just kind of a diagram of how this might work in practice. To create a filter, they can be done through any application API federate. So a value federate could create filters, or a message federate, or it can be done directly through the core. And the function you see on the screen, basically a register source filter, takes a filter name. This is mainly for reference. It can be left blank. the source endpoint. This is the most important one. And then you can also define types. Types are not used that much, mainly for custom filters that do packet translations, where you want to know kind of the type of packet that it's expecting and the type of packet that it's sending. And this can be used if you have multiple filters tied to a source. The name can be null. One will just be created, and this returns an identifier code that you can use for later reference. There's another form in the APIs that takes basically just an endpoint and doesn't worry about the types or name. Filters can also be created through a JSON file input for configuration. And you can, in a federate, it then creates a list of the actual federate objects, and you can query these and get them out at a later time. To specify an operator, you give it an ID and an actual filter operator object. The operator object is defined in the core data.hpp file. It's basically an abstract class with a single overloaded function, namely a process. And this takes a unique pointer to a message. So you send a message in, you get a message out. Using modern C++ move semantics, you can basically move the same message in and move it out on the other side. So there's a limited overhead in the processing there. Or if you want to, you can create a new message. Basically gives the overload the option of what it needs to do. If it has to generate a whole new packet, or it's just modifying some small thing on the message. There's a number of simpler operators which operate on specific parts of the message. So you can operate on the time, the message data itself, or the destination. And these take simpler function objects or callbacks from the user. And these are how you would often specify custom filters. The other API is in filters.hpp. This is an object which wraps around the filter calls in the core and federate. And you can make a source filter, and these allow a number of predefined types. And they also have a set function which allows you to set properties on these filters. And this can be done via numerical values or string values. There's a number of different types that are defined in the API. There's a custom one which allows you to specify a user-defined operator that operates on message. The delay is one of the simpler ones. It basically delays all messages by a certain amount of time. It has a property named delay. This can be specified as a double in seconds, or you can specify it as a string with some time units on it. There's a random delay, which allows specification of a number of different types of distributions, and it takes two parameters. Some distributions only use one or none of the parameters, but you can specify the parameter name via any of the values you see on the screen there. Other filter types include a random drop filter, which will basically drop a message and not forward it on. You can specify a probability from 0 to 1 that the message will be dropped, and this is modeled as a uniform distribution. The reroute filter allows the alteration of a destination of a message. You can specify a new dest property, and this will create an updated destination. And this can be a function of the original source and destination. So it uses a string replacement for some simple processing on that if you want to use the filter for multiple different endpoints. It also specifies a regular expression condition that it will only be filtered if one of the conditions specified here is matching. And this takes a regular expression as available in C++. There's also a clone type, which will copy a message and send it on to a delivery address. Looks like I misspelled the add delivery there, but I will correct that before too long. And you can specify it to deliver to a specific endpoints or multiple endpoints. There's also a cloning filter object, which you can tie to multiple different sources and destinations if you want to clone a whole bunch of different things. And this is used in the recorders and tracer applications. And to end with, I just want to make the comment that filters are a new concept in HELICS, and the interface is likely to change in the future as people start to use it and provide feedback, and any feedback on these is appreciated, and how to make them more usable and more functional in HELICS, and how to make it all work better. And that's all I have, so if you have any questions, feel free.
Hi, this is Priya TM from PNNL. I was wondering if you have an existing example that uses filters right now.
There's a lot of the test cases that do, but we do not have any examples that use it yet. It's something we're working on.
Okay, thanks.
So this is Shri. Quick question. So do the filters only work with message federates, or can they be used with other federates as well?
Right now, filters only operate on messages. You can create them as part of a value federate if you so want to, but they don't operate on values.
Okay, all right, thanks.
Excellent. Well, thank you, Phil. Appreciate it.